Hello, good afternoon, everyone. First, I just wanted to apologize for Monday. Because of the internet outage, we had to cancel class. I'm not sure how we'll make it up, but hopefully we'll be able to squeeze in all the material by the end of the quarter. And so that may mean sort of cramming a little bit more or cutting out a little bit of the material, but hopefully we should get through all of the topics listed in the initial syllabus. So a couple announcements for the beginning of class. As a reminder, the second homework is due today by the end of the day. And so please make sure to get that in. And if there are any questions, you can feel free to email me. I'll try to make myself as available as possible today, especially given that office hours on Monday was also canceled. One of the challenges with this course for me is, since it's my first time with this course, it's hard to have any expectations about what the grades are going to look like. And so I had actually been planning that if the grades were lower than I expected, that we could do some curving. But actually for homework 1, the grade distribution was fairly reasonable. So that's not going to be curved, but we will still sort of look at every individual assignment and test individually to see if there's a need for that. So I can't say anything certain about whether or not the midterm or the second homework is going to be curved. So for the first homework, everyone should have received your grades. And in terms of grades for the midterms, we haven't started grading yet, but hopefully we'll be able to start sometime this week and finish shortly thereafter. So I want to talk a little bit about the projects. So again, my apologies. I didn't make this clear. In terms of the submissions, you only need 1 submission per group. So I got lots of emails actually from a bunch of different people who were worried about the fact that they didn't submit it, but team members did. So you don't have to worry about any of that. Only 1 submission needed per group. So I don't think there are any issues there. The other sort of big feedback that I got was that the project abstracts, it wasn't super clear in terms of the direction and what to provide for the submission. And part of that on our end was that we wanted to leave the topic exploration intentionally vague so that everyone could kind of explore the topic in general and focus in on the particular aspect of the topic that they were interested in. But I realized that also made things difficult in terms of understanding what it is to exactly do and to submit. And so I think what we're going to do is, for the interim and final deliverables, right? So you've got the project outline and the project report. We're going to try and do our best to provide a better outline and guidelines about the content of the submission, while trying to stay away from what to think about in terms of the topic. And so hopefully that'll provide a better goalposts for this. So I appreciate everyone's feedback, and hopefully we can make it a little bit more clear in the future. And I'll actually try and reach out to the previous professor for the course to see if there are some examples for the deliverables that we can use, so that you guys can reference that. I'll also mention one of the things that we're going to be doing for the project rating. Um, Again, this is sort of uh, coming up based off of feedback, is that I totally understand that these are sort of difficult times and that it's hard to communicate, but you do have to participate in the project. And so we're going to be implementing a peer review grading system that's going to be taking into account those that aren't participating, and that will also sort of account for the fact that maybe you only have 3 people working on the project instead of 4. So we'll be able to take that into account in the final grading as well. And so if you haven't been communicating with your group, please make sure to do so. This you're making life more difficult, not just for yourself, but also for your group members down the line. Okay, and the last thing is something that I know doesn't apply to 99% of you, but with regards to plagiarism, yeah, don't do it. This is going to be your only warning. Everyone knows what plagiarism is. If you're copy and pasting stuff and you're not citing it and you're not quoting it, that's plagiarism, and we can't. You're literally tying my hands here. I can't sort of be forgiving about this. I really hope that the material is more important than the grades, and I think that's we're trying to reflect that in the flexibility. So I'm much rather you turn in things late, and we can be again flexible with that, especially given these circumstances, than to do any sort of plagiarism. So that's, again, sorry, I know this doesn't apply to the vast majority of you guys, but this is going to be the only warning that you get for doing that. Okay, so that's basically most of the class announcements for today. Before we move on to the lecture material, does anyone have any questions? You can feel free to speak up or type out in chat. Okay, no questions. Just me talking by myself over here. So we're gonna pick up where we left off, which was quite a while ago, right? Because we missed one lecture, and also we had the midterm. But before the midterm, we were sort of wrapping up nuclear energy. So we'll talk about that a little bit today, and then move on to the main topic, which is learning about our electricity grid, which is a very it's a pretty interesting topic. It's very interconnected with everything that we've talked about, and we'll have to go over a lot of the sort of high-level insights about the grid as it relates to interconnecting all the stuff that we've been talking about for end users, and all the things coming from the generating like electricity producers, and it turns out there's lots of interesting dynamics happening on the electricity grid, that at the very least it'll be good for everyone to at least understand where or how the electricity system works, so that you have a sense of how it is that you get the electricity that you use every day. All right, let us soldier on. So thinking about environmental impacts, for nuclear power. From a carbon perspective, I should say that nuclear power essentially is emissions free, right? So similar to sources of renewable energy, the main, or I should say, unlike fossil energy, despite the fact that what it's doing is essentially the same, right? Which is heating up water, spinning a turbine. You don't need to combust any fuel to do that. And so from an emissions perspective, nuclear energy is basically as clean as it gets, similar to renewables. But it does have a byproduct, which is nuclear waste. And unfortunately, it's a pretty difficult problem, but it's both politically and socially, as well as sort of technologically. So there's no country in the world that has really implemented a good system for permanent disposal of the spent fuel and radioactive waste. I think the one that's most widely favored is geologic disposal, where you basically carve out a specific area of land that can essentially house nuclear waste. And so you guys may have heard of some plans to do that in the United States. I think there's a specific mountain range where they're trying to do this. Hang on. There we go. But actually, the vast majority of nuclear waste today isn't being stored geologically. It's kind of just being stored on site. So they have these essentially giant sort of swimming pools that house all of the nuclear waste. And so it's definitely a controversial topic, and one of the biggest problems is that no one really wants it to be close to them, and so it's been a struggle for the nuclear industry to figure out a sort of permanent site to store the nuclear waste. So here's a schematic of essentially a nuclear waste storage area. Let's see. Okay, so there's a question. Oh yeah, so a couple comments. Yucca Mountain. Yeah, that's the one that's being talked about a lot for nuclear storage. And there actually have been plans and developments of that site. But as far as I understand, it's not actually storing anything right now. And then another question, if we don't know how to deal with the waste, why do we still use it? Other reasons rather than the energy needed. Well, that's probably one of the big reasons. So there's a couple big benefits of nuclear. So one, it's really clean. And then two, from an actual sort of technology perspective, it is able to turn on and stay on for a really long time. And because of the size of a nuclear plant, it produces so much power. It's one of these things that is really sort of useful for what's called baseload power. It's essentially useful because you can keep it on and provide lots of power for long periods of time. And so when we're talking about capacity factors, nuclear is far and away the highest average capacity factor in the country. In other words, it's the one that stays on for most of the time. The average capacity factor of nuclear plants in the United States is definitely well over 90%. Whereas even really high capacity factor like coal and maybe even natural gas plants are maybe 80%. So nuclear plants that's another sort of big benefit. And then the last one is from an economic standpoint. So we've talked about the cost of building a nuclear plant, which is pretty bad, all things considered, because they take so long to build. There's all these regulatory requirements. But once it's operating, it's super, super cheap because the fuel is way, excuse me, is way cheaper than your fossil fuels. And so we're going to talk a little bit about how the electricity system chooses what power plants to turn on, and the order in which they turn on later today. But as sort of a precursor to that, I'll just say we prefer renewables on first, and then the next thing that usually gets dispatched is a nuclear plant. Yeah, and so definitely lots of benefits, but waste is one of the big drawbacks. Yeah. So U.S. nuclear waste storage sites, so you can see that here. The green dots are sites where nuclear fuel is stored. A lot of these are just at the nuclear plants themselves. Yeah, so 100 million US gallons of radioactive waste and 2,500 metric tons of spent fuel. So the gallons of radioactive waste is usually just water that's been irradiated. And then the metric tons is referring to the actual material that has been fissiled. So this is the one that I just mentioned, Yucca Mountain in Nevada. So it was way back in the 1980s that it was designated as a nuclear waste repository. But yeah, after, even despite lots of money and many years to develop it, no waste is yet being stored. Definitely one of the most controversial aspects of nuclear power. And I think whereas safety is somewhat of a concern, I think from a sort of public perception standpoint, I think nuclear in general is quite safe. But the nuclear waste handling is probably a perception piece that is kind of reflected in reality. Yeah, and so because of public backlash, it's been difficult to try and open Yucca Mountain, and actually the Obama administration decided to terminate the program while looking at other waste sites. And then one of the final issues that is pretty unique just to nuclear power is this idea of proliferation. And so nuclear proliferation is the worry about the spreading and use of nuclear weapons. So technologies for peaceful nuclear power programs will somewhat overlap with those used in production of material for developing nuclear weapons. And so one of the biggest concerns is that countries with the intent to proliferate can basically hide that through saying that enrichment is for nuclear material for power production. So that's one big worry. And the other one is that if you are operating in facilities that don't have a lot of security, theft and transfer to those who want to take advantage of using nuclear weapons would be another big risk. Oh, sorry, I see a question. Is Yucca Mountain the only storage site of its kind? Um, if all of the US plants store waste on site, do we know how long that is feasible for? Yeah, good questions. So Yucca Mountain is kind of unique because it was designed to be big enough to house all of the nuclear waste or the vast majority of nuclear waste in the US. And so you could just ship it there and store it. So there are definitely other disposal sites, but I think that Yucca Mountain is the only one that was of that size, or at least it's the biggest of the disposal sites. And then in terms of storing the waste on site, um, how long is that feasible? So actually, I think that they're technically designed to be feasible across the lifetime of the plant. Um, and so a lot of them will end up shutting down before they run out of storage space, but that's not true for all nuclear plants, so some of it ends up needing to get disposed. So on average, I'm not sure exactly how big of an issue that is. So we've talked a little bit about the nuclear power supply chain. And here, this includes everything from mining and milling to enrichment, fabrication of the fuels, and then actually using it in the nuclear reactor, and then um, storing the fuel, and reprocessing fuel for the ones where you're reusing some of the waste. So pathways from going from nuclear power to nuclear weapons. If material gets stolen in certain parts of the supply chain, that can be a risk. So you can also covertly sell the material. You can divert a little bit of the material, um, and that can be pretty difficult to keep track of, especially if it's like a government level operation where you are promising not to build weapons, but you're in charge of managing the overall nuclear power. And then there are some scenarios that people are worried about where if you've signed on to the Non-proliferation Treaty, in order to get nuclear technology, in order to get produce power from nuclear, and then you use that to stockpile some of the material, and then you just renounce yourself from the treaty, and then use the technology you gained. So that's an additional worry. This is a diagram comparing countries with nuclear power versus country with nuclear weapons. And so in the top one, you can see there are a number of countries in the blue that have operating reactors and are either building or planning to build new reactors. In the green, they don't have any reactors operating currently, but are either building them or planning to build them. And then the bottom right. Okay, so I see another question. Who enforces the Non-proliferation Treaty? So I'm going to get to that actually in the next slide. So then countries with nuclear weapons, it pretty closely mirrors the countries that have nuclear power. And so the ones that have weapons that are not part of the Non-proliferation Treaty. It's basically just India and Pakistan, which you can imagine is probably a little worrying. But actually, there have been a couple countries which have renounced use of nuclear weapons and are essentially divesting from them, and so getting rid of their nuclear weapons. And I guess that's kind of a step in a good direction. So the Non-proliferation Treaty. So what is it? It is an international treaty meant to prevent the spread of nuclear weapons and technology, and to promote cooperation for peaceful uses of nuclear energy. So it is the only sort of multi-state treaty with a binding commitment to disarm nuclear weapons. So 187 parties have joined the treaty, including 5 of the nuclear weapon states, right? So excluding India and Pakistan. One of the promising things is that more countries have ratified the Non-proliferation Treaty than any other arms agreements, which is, yeah, I think it's a testament to how important the treaty is, and how seriously a lot of countries take it. But in terms of, so the question that was asked in chat, who enforces the Non-proliferation Treaty? At the end of the day, it's kind of a voluntary basis, right? There are organizations that do things like do verification and monitoring, but it's not as though any of these organizations has the power to stop an entire government or country from developing the nuclear weapons. And so to that end, it's pretty similar actually to a lot of the climate change agreements, where it's essentially a somewhat voluntary agreement that you're going into. Okay, let's see. I'm going to skip a slide actually. Is nuclear power a good way to address climate change? So again, some of these benefits that I was just mentioning: zero carbon power, potentially widely available in the sense that the fuel itself is really cheap and pretty widely available. Scaling wise, it's really nice because you have a lot of the fuel, the actual plant can be built to be fairly large, or actually in more modern days, people are starting to talk about what are called modular reactors. So they can be built down to be fairly small. And then in terms of the fuel reserve, it can be available for hundreds of years. And so it does suffer from similar types of issues in terms of limited resource availability over some amount of time as fossil fuels, but it can still stretch out for a fairly significant length of time. In terms of how many new nuclear plants are needed to reduce carbon emissions, so there's a couple different trajectories, and I guess we don't have to get into so much detail about what all the trajectories look like, but I will say that when you look at reports from like IPCC and similar types of things, So for example, this next slide is a DOE scenario for low carbon future. Basically, all of these futures that people are looking at suggest that we need a lot more nuclear in order to achieve our climate targets. And the reason why that happens is you have a pretty hard time being able to provide electricity just from wind and solar and from renewables, where you do want a low carbon future because of the intermittency issues where the sun doesn't always shine, the wind doesn't always blow. So you need some sort of stable power supply, and the one that's kind of easiest to turn to that is totally clean is nuclear power, despite that it has many other sort of drawbacks. And so this is just one example, but many projections of getting to low carbon futures has pretty significant developments in installation of new nuclear power. And that's definitely kind of the opposite trend that we see happening these days. Like I was saying, in Japan, for example, they've shut down the nuclear plants, although they're, I think, trying to get back to some of them. And then in Germany, for example, they've shut down their nuclear plants. And in California, even in our state here, we have shut down a number of nuclear power plants over the last decade or so. And actually, there's only one nuclear plant left in California. The Diablo Canyon one down near San Luis Obispo, that one is slated to retire in 2025. And that power plant actually provides something like 20 to 30% of the power in the state on average. So you can imagine that, well, are we going to be able to replace all of that with just renewable energy, or are we returning to more fossil-based sources? And this push towards retiring the nuclear, at least from a climate perspective, is not so great. And that's not to say that we should ignore some of the other issues with nuclear, such as the ones that I was just pointing out. But it is an important issue that a lot of climate scientists are concerned with. When it comes to thinking about the technology, there are pretty different views for nuclear. So in the Obama administration, they wanted to really be able to look at all options and sort of gauge what makes the most sense, guided by science. Trump administration actually does also support nuclear, but I think it's more sort of just on a technological basis. They want to revive the coal and nuclear industry. The Federal Energy Regulatory Commission, which we'll talk a little bit about today, there was a nuclear plan that was put forth by the Trump administration and was rejected. So this particular incident was to bolster coal and nuclear power plants with subsidies, and that was proposed in January 2 years ago. And essentially, it didn't really make much sense to do this subsidization, and as a result, failed to pass the Federal Energy Regulatory Commission, which is in charge of developments in the electricity sector. And so you can take a look at that in more detail. I have a link here. Okay, and this goes back to what I was saying. This is another sort of scenario diagram of compliance with reducing climate change impacts. So 6DS and 2DS, those are 6-degree scenario and 2-degree scenario. And what you can see in the sort of purple is that in programs that have lots of or a lot more climate mitigation, right? So 2-degree warming instead of 6-degree warming, you have substantially more nuclear. Okay, so is nuclear green? So Breakthrough Institute has suggested that it's one of the best things to address climate change. You can rapidly scale it up. It's lower cost than renewables. Maybe I might disagree a little bit about that one, especially these days where particularly wind power is quite a bit cheaper. It may still be technically economic over the course of its entire lifetime, better than solar. But again, those numbers are changing, and it's not only about the marginal cost, but the difficulty in installing new capacity is so big. If you remember from last lecture, these things are taking decades to build now, and that's an important consideration as well. Yeah, so others still see renewables as the best route to a near zero carbon energy system. But again, these things aren't so black and white. I think there's not really a silver bullet, and you'll probably need a mix of everything to get to what we need. Okay, so that's a wrap up of the nuclear power. So let's go ahead and dive right into the electricity grid. There's a lot of interesting stuff to talk about here. So this is the basic layout of the grid, and I'm sure that lots of you guys have seen this infrastructure before, but we've essentially talked a lot about this portion of the grid, right? So the generation assets, power plants, different sorts of power generation assets that produce electricity. And we've talked a little bit about end use, with efficiency, and even, sort of in the homework problems, we say stuff like, oh, you use electricity as kind of your final energy, right? But we haven't talked so much about all the stuff that happens in between and some of the operational aspects of the grid, which are all sort of fairly interesting. So we can divide the electricity grid essentially into 3 major components. So 1 is generation, 2 is transmission, and 3 is distribution. And so the main way that I like to explain this to people for differentiating, so in the transfer of electricity, transmission and distribution systems. So technically, and which we'll talk about, transmission operates at really, really high voltages, and they carry higher capacity and transfer electricity over really big distances, as opposed to distribution, which is much lower voltage. So transmission infrastructure is all that stuff that you would see, the really big electric towers, the big metal ones that you'll see on the freeway, as opposed to distribution infrastructure systems are the ones that you see as you sort of drive around town. You see those wooden poles. And so that's the sort of visual, easy way to distinguish between transmission and distribution systems. Okay, so before we talk about that, I wanted to speak about one of the most critical components or operational aspects of the electric grid, and that is balancing electric load. So if you go into your kitchen and you turn on your light, or you go into your living room and you turn on your TV, essentially what's happening is you are asking for electricity, right? So that increases the demand for electricity. And And at the same time that that's happening, some power plant somewhere out there is spinning up a little bit more to provide that electricity. So the main point is that electricity, for the most part, it can't really be stored, okay? It has to be used at the same time that it's produced. And so the way this works is that in the US, for example, so grid operators operate at a frequency of 60 hertz. So that's the frequency of the electricity in the electric grid network. And so we're not going to get into the physics of all of this, but essentially what happens is if you have too much electricity, then the frequency increases. Oh, I see I didn't complete this bullet point in my slides, but what happens if you have too much electricity? If the frequency gets too high, it's going to end up turning off some power plants. Your system becomes unstable, and that can mess with a lot of the existing infrastructure in the system. You might lead to equipment failure. The frequency can start to oscillate, in which case you're going to get, how might I describe this? So if you had if you were thinking about electricity as like water in pipes, what would be happening is like the pressure of the water would keep changing. And as you can imagine, that's probably not really good for things that can't handle sort of variable amounts of load. If you have too little electricity provided, right? So if the plants aren't spinning up to maintain the frequency, then the frequency will drop. And this is going to cause power plants to turn off. And so you get this big chain reaction, and that can lead to something like a blackout, which is one of the things that, at least in the United States, grid operators try to avoid as much as possible. Okay, so that's one of the really key things to remember about the electricity grid, is the concept that you have to produce electricity to the same quantity and at the same time that electricity is being demanded. So this next slide, oh, actually, this is not in LA. This is in Northern California. Sorry, I'm just realizing another typo here. So this is a pretty common diagram that you would see in power systems engineering, for example. This is what we call a load duration curve. So what are we looking at here? So this is approximately over 1 week in Northern California. And so these cycles are the amount of electricity being demanded basically every hour of the day. And so why does it look like this? So these peaks that are happening are like, okay, the troughs are like everyone is going to bed, turning off their lights. That's when you have the lowest energy demand. So that is the trough here. And then as folks wake up, turn on their lights, go to work, turn on computers, turn on your air conditioning, all that good stuff, your electricity demand will increase over the course of the day, and then will sort of decrease over time as you sort of wind down. And then you've got this sort of cyclical process. Weekends, right at the end, I believe this is Sunday and Saturday. Weekends tend to be a little bit lower. You don't have as high of electricity demand. And you're going to get variation from day to day, right? Not everyone uses the same amount. And also one of the really big things that contributes to variation, at least seasonally, is temperature. And so in the summer, you tend to have really high loads, at least in California, because people are running their AC. In a lot of East Coast areas, summer and winter are both pretty high because people are doing lots of heating as well. So anyone who's doing electric heating is going to contribute a lot. Um, and yeah, and so over the course of the week, this is the really sort of typical sort of shape of the curve that you would see for load duration. And then people will often combine this with what's known as a dispatch curve. So this is the same. I think it actually includes one extra day here, but this is 8 days of that same week in Northern California, and what you'll notice is that the overall shape here should be almost the same. It's actually not going to be quite the same for some artificial reasons, which I won't talk about. But essentially, this shape and this shape are going to be identical. But now you can see it's filled in with all of these colors. And what the colors are representing is actually what is the power source that's providing the electricity. Okay, and so you can see during the day, right at the top here, you've got this sort of greenish gold color, and that is from solar. But you can only see the solar happening during the day, and it sort of picks up a lot in the middle of the day, and then you don't see any sort of happening at night. And then in the screen here, you have wind, which tends to be quite a bit thicker in the night periods where there's more wind. And so this dispatch curve is sort of analogous to the supply or to the demand side, where you're looking at how much electricity is being demanded, and it provides how that electricity is being supplied. Okay, and so as I was mentioning with the solar and wind, so what does this mean for renewables, right? So the sun doesn't always shine and the wind doesn't always blow. And so in order to provide energy, we have to employ other sources of electricity. So how are we supposed to deal with this issue? So one is that you have to employ other sources of electricity generation. And that kind of begs the question, well, how do you cut out fossil fuels then if you need other sources? And so nuclear, for example, might be one case of that, or one possible way to alleviate this issue that we call intermittency. The other way is that you use energy storage. So we have talked about some of these before, so pumped hydro and geothermal, but a lot of that has already been sort of used up. There's not that much new resources available, and it's hard to co-locate them because they are dependent on the geography. And the other one is battery storage, but that's also really expensive. So from the economic side, can be difficult to try and get that to integrate in. So one other issue that that I want to talk about with renewables is something called net metering. And so this is a concept specifically for distributed energy. So this is talking about like solar that's on your rooftop as opposed to the big utility scale solar. And so what ends up happening is if it's in your home or school or business, if it's like local and it's not going through the transmission and distribution system, you end up just using electricity that's being produced from the sunlight, which means that you draw less electricity from the electricity system as a whole. And actually, you could be producing more than you need, in which case you actually produce extra electricity that goes back onto the grid. Let's see, I see a comment. We could also use photothermal conversion, so we not limited by sunlight time. So I think you're talking about CSP. If not, you can correct me. And so that is one potential source where you're essentially able to store some of the energy as heat. Um, but it's not. So one of the issues with that is that it's not super efficient, which is a problem, and the other one is that it's fairly expensive. So we don't see so much of that. Um, yeah. Okay. So going back to this net metering. Um, so essentially, what this does is it's reducing the supply of electricity that's needed to provide power. And that has led to a pretty interesting issue, which some of you may have heard of before. And so this is called the duck curve. So I was showing the load duration curves earlier. So this is a load duration curve for a single day. And you may expect it to look, if you remember, something like one sort of peak followed by one sort of trough. Um, but what has ended up happening um, in California is this sort of phenomenon. Okay, we call it the duck curve because it apparently looks kind of like a duck. Um, so with net metering, what ends up happening is that you reduce the effective demand. And so this is a real sort of net load curve from the end of March every year. And so in 2012, it looks something like this. And then more and more like distributed solar, so solar on people's rooftops, was getting installed over time. And so the amount that they're demanding from the electricity grid sort of decreased in 2013 and then decreased in 2014. And you can see year on year that that the total demand is decreasing, and that is leading to some pretty interesting issues for our electricity system. So on the one hand, you might think, well, it seems like it's good, right? Because we're using more solar, um, and you're reducing sort of use of fossil fuels. And yeah, so that's definitely true to an extent. But actually now you are forcing the grid to deal with some pretty interesting issues. So here the demand starts to fall really quickly, and so what that means is that you've got a whole bunch of power plants that are on, and suddenly solar is getting introduced into the system, and you need to start turning those power plants down. And then you have probably even a bigger problem where all the solar starts disappearing and the demand ramps up really quickly again, and now you have to turn these power plants on. And so why is that an issue? So power plants have what are known as sort of ramping capabilities. It takes a different amount of time to turn on a power plant and to ramp up or ramp down a power plant. So you can imagine, so gas turbines are pretty fast to ramp up. So we can see here, basically, so for a gas turbine, the relative time it takes for it to ramp up to its power capacity is relatively quick, as opposed to a steam turbine, which is relatively slow. And so why is that? With a gas turbine, you basically pressurize the gas, send it through the turbine, and combust it, and you're kind of good to go. Although there are issues with the temperature that it's operating at. It could take time to heat up, and so it's not necessarily instantaneous. Okay, sorry. There's a question on the y-axis on the dot curve is the solar energy um, or the power plant. Sorry. So this is the total demand from like us, from the general population, and then it is being provided energy from the grid, and um, so this isn't referring to production of solar energy or power plant energy. Um, it's what we demand. And the reason why you see this changing over time during the day is because there's more and more solar. And so the electricity being supplied from the grid decreases because you don't have to provide the electricity that the solar plants are producing. Um, Yeah, and so with steam turbines, it's much slower to ramp up because you gotta heat up the water and boil it, right? And that takes time. And in addition, if you turn off a power plant, you can't just turn it back on right away. It needs to cool down to a certain temperature. They have to stabilize it before turning it back on and ramping it up back up. So that could take a couple hours. And so you can imagine that if you run into this issue where a power plant maybe has to like turn off here and then it hasn't had enough time to undergo all the proper procedures about cooling down and the shutdown startup procedure, like maybe you can't turn it on in time to increase the ramp rate. And so instead, maybe you'll choose not to turn off the power plant, and you'll still try and sell some electricity at a loss, right? Because it's maybe it's more expensive in certain hours. So that's those are the sorts of issues that we're seeing from having more and more renewables on the grid. Is that essentially at a high level, it's harder for the grid to accommodate higher levels of renewables. And then the other thing is that when your power plant are operating in these flat areas, right, at their capacity, they actually are designed in a certain way to be operating most efficiently. When the power plant is ramping up and down a lot, you actually have a lot worse emissions. And so there's actually been a study. This was actually someone in my grad school, a paper that they published where they looked at systems that have more and more renewables. So this penetration factor is the higher the penetration, basically the more renewables were on the system. You actually had an increase in emissions, even though more electricity was being provided by renewables. And so the reason why that was happening is because you would start to need more and more power plants ramping up and down to um, to meet that. And so you ended up getting higher, in this case, NOx emissions, so nitrogen oxide emissions. Um, and so I definitely don't want to be sort of disingenuous here. That like this is kind of a more extreme example, and it's not often that you have higher emissions with more renewables, but it is something that can happen. And these are the types of things that we want to be sort of cognizant and keeping track of. Okay, why don't we take a quick break? I've been droning on for an hour now, so let's reconvene in 5 minutes. And in the meantime, I can take questions. Um, yeah, so I see a question. Do you know how long it takes for nuclear power to ramp up in relation to others? Yeah, um, good question. So it's by far the longest ramp up time. And actually, when I was speaking before about having a really high capacity factor, you basically don't want to turn off a nuclear power plant. The all one of the reasons why it's at super high capacity factor, like 95, 96, 97%, is specifically because you don't want to turn it off. And they do, the only times that they really turn off the nuclear plant is in case of emergencies or when they need to do like annual maintenance. And nuclear plants, so the ramping is slow. The ramping is kind of similar to coal plants because it takes time to heat up the water. So you might get, if I remember the figure off the top of my head, I think you can get like 40% of the capacity up in terms of ramping in about an hour. But from a startup shutoff perspective, a nuclear plant can take several days to between when you shut it off and when you can start it up again. So definitely a really, really long time. I see a question, is the outline due today? I don't think so. Hang on. Let me take a look at the syllabus. Yeah, so I see some people saying a week from today. Yeah, that's right. Yeah, it'll be due next week. Although, yeah, let's see. I know I'm kind of winging it here, but how would you guys feel about having more time on the outline? We can. I'm kind of looking at the overlaps between uh, between the all the homeworks and also some of the issues that folks were talking about with the groups. And I'm looking at how much time you have in between then and the final project. Yeah, why don't we push that back? Let's see. We can do one additional week, so it'll be due May 20th. I'll make an announcement on Canvas for that. I think that would make a little bit more sense. Yeah, I think probably one of the reasons why you were saying it's due today is you might be looking at the old syllabus. We pushed back everything 1 week because I wasn't able to get mentors for all the projects by the time that we had initially wanted. So we pushed everything back a week. And so there's actually an updated syllabus from the one that was posted at the beginning of the quarter. And I'll update it again and make an announcement on Canvas. Okay. Yeah, I actually, for some reason, I had in my mind that it was actually due a little bit later, and I think that sort of just makes sense given where most folks are at. So, again, sorry about kind of winging it here, but at least now you'll have more time. Okay, so let's push on ahead. So going back to thinking about the basic layout of the grid, so now that we have a better understanding of some of the operational aspects, I want to go into a little bit more detail about each of these sections in generation, transmission, and distribution. So I'm not going to go so much more into generation because we've already talked about power plants sort of at the individual level. But I do want to revisit a little bit of stuff here. So this is a diagram that I've shown before, showing where all the power plants are in the country. And so again, the color denotes the fuel type. And so you can see some trends I'll point out. The Pacific Northwest is really well known for having lots of hydropower, so that's in the green, and their dots are actually pretty big, which indicates the size of the power plant, the capacity. In a lot of the sort of more dense population centers, we have a lot of pink, which is renewables. So you can see that on the West Coast and on the East Coast. It's definitely better on the West Coast in terms of the sunlight that's basically available. And so these ones operate at higher capacity factors often than the ones over here. In gray, you will see a lot of that happening in the middle of the country. And if you remember back to the renewable resource lecture, a lot of the stuff in the middle of the country has high wind resources. So the gray is wind, and the reason why you see a lot of it sort of happening here is because of the availability of wind in that area. And you'll see a pretty high density of blue, more on the East Coast than on the West Coast. You won't see any blue in California, and that is coal power. So used to be a lot more dominant, less so now, but still providing a very large amount of power in the country. And then the other one that you'll see a lot on the East Coast and not so much on the West Coast is the orange. So there's one orange one that's kind of hidden behind some other dots, I think, over here. Other than that, most of the nuclear plants have been shut down in California, as I was mentioning, and you can see where they're located sort of on the East Coast. Okay, so there's this question here. If you remember back to the load duration curves, right, we're going up and down every day, which means that not all the power plants are turned on. And in fact, I shouldn't say most, but a lot of power plants are not turned on all the time. And so who gets to decide which power plants are turned on to provide the electricity? Like how does that happen? So normally we would have this little game that we play, but I unfortunately couldn't figure out a good way to do that online. But the main gist of the game is if everyone is a power producer, so if we basically assign you to be a nuclear plant and another person to be a natural gas plant, another person to be a wind plant, and then solar power. The order in which you turn on is based off of something called economic dispatch. So if you are a nuclear plant or a natural gas plant or any power producer, you operate in a special type of market. And essentially how that works is you say, I promise that I will produce this amount of power for X dollars. And then someone else will bid into this market and say, well, I will produce this other amount of power for Y dollars. And what ends up happening is all these bids go into a central operator. And so in California, that operator is known as the California Independent System Operator, the ISO. So we call it CAISO, the California ISO. And that independent system operator, they actually operate in Folsom, pretty close by to us, and they take in all of the bids, and then they will order them in terms of the bids that people are making. And so the first people to turn on are the people who bid at the lowest price, and then they will get dispatched to meet to provide electricity on our grid. And then if the electricity that they're providing is not enough, then the system operator will turn to the next highest bid, and then to the next highest bid, up until you get enough power. So this is what is called a dispatch order curve. So this dispatch curve is looking at how much power you can produce. And let's say you need a total of 100 gigawatts of, or say, no, sorry, 150 gigawatts of power. So I need up to here, and I'm going to turn on all the plants to the left of 150, okay? And so it's going to be a whole bunch of like coal plants, a couple biomass plants, some nuclear plants, and then all of the pumps, the solar, the wind, and the hydro. Yeah, okay, and so that's the system today of how you dispatch electricity from different power plants, and that is how you get selected to turn on. Okay, and so now you might be asking, well, how do you decide to turn on, and why would you turn, and why would you bid into the market? Or I guess, what's the incentive? So it turns out the most strategic bid in this competitive system that you want to bid is the marginal cost of producing the electricity, right? And so if I bid under what it costs me, then I could be losing out on potential revenue, right? Or yeah, so okay, hang on. So if you bid at your marginal cost, then you will never lose money, because if you get turned on, I should say first that what you get paid. So if I say at 150 gigawatts, the amount of money that gets paid isn't what you bid. The amount of money that you get paid is the last bid of the power producer in the system, and that's known as the clearing price. So if it was the 150 gigawatts, then everyone to the left of 150 gets paid about $1.80 per MMBTU. Okay, so the last guy who turns on, he is getting paid the same amount that it costs him to produce the electricity. So he doesn't actually make any money, but everyone to the left of him does make money, because it costs this guy and all of these guys a little bit less than what they're getting paid. And so you never want to underbid your marginal cost, because you might get dispatched to produce electricity, and it would cost you more to produce the electricity than what you're making. So you never bid above your marginal cost. And so in this system, right, it's a purely sort of economic market-based system that's going to turn on based off of fuel costs. And actually, one of the big benefits of doing something like a carbon tax is that you would be able to internalize some of those costs. And so if you if you added a carbon tax, you could actually switch the dispatch order, and it might cause like natural gas plants to become less expensive than coal plants. And so those guys would turn on first before coal plants would turn on. Yeah, and so hopefully this concept is not too confusing to you guys. But again, the basic way that power plants turn on is cheapest first, most expensive last. Yeah, okay, a couple questions coming up. Who owns the power plants? Are they privately owned? And that's why they can set the cost themselves. So yeah, so it's a little bit complicated, and it depends where you are, and we'll talk a little bit about that later on. But the power plants in certain, so there's like regulated areas and unregulated areas. In deregulated areas, so you can't own the generation, transmission, and distribution. That would be what's called a vertically integrated monopoly. And then you could kind of like set your prices, right? And so the owners are going to be independent. Yeah, and so you can kind of think of them as sort of private owners. And then there's a question: is this essentially a supply curve? Yeah, exactly. This is exactly a supply curve. Yeah, and it's broken down by fuel technology. Okay, so that's enough about the generation operation aspects. So here we'll talk about transmission. Nothing too detailed here, right? So electricity transmission operates in three-phase alternating current. It's transmitted at really, really high voltages, 110 plus kilovolts, so 110,000 or 110,000 volts. And you do that to reduce line losses. And they're pretty serious cables. This is an aluminum cable that you would typically see in these systems. And the way you get it up to the high voltage from the generator is through what's called a transformer. So transformers are going to step up or step down the voltage. That's essentially what the equipment does. To give you a sense of what the transmission grid looks like in the United States, there's about 160,000 miles of high voltage power lines. There are essentially three independent, they're known as interconnections in the continental US. You've got the Western Interconnection, the Eastern Interconnect, and ERCOT, which is the Texas Interconnect. Texas has basically its own grid. So everything within that interconnection helps with essential reliability. And you don't get much electricity flow between the interconnections. You can almost think of them as their own sort of electricity grid. There are what are known as interconnection ties, which allows for electricity flow through the interconnection, but it is really, really low quantity and pretty unusual. When we talk about modeling and looking at this type of stuff, we typically treat these as independent. There's also a reliability corporation. So this is formed by electric utility industry to increase reliability of the bulk power system. And this separates the interconnect, at least the Eastern interconnect, into what are known as sort of balancing areas. And the NERC regions, along with the Federal Energy Regulatory Commission, are the ones that are sort of responsible for setting policies and standards for operation. So a lot of the rules that happen are sort of formed by this corporation of regions, as well as the Federal Energy Regulatory Commission. Okay. So then sort of zooming in on the last third of the electricity system pie is thinking about the electricity local distribution system. So this is all the stuff that you're basically seeing in the neighborhood. So it starts at the substation, which is where the big sort of transmission lines have transmit the electricity into these substations that have essentially these step-down transformers which lower the voltage. There is one substation in Davis. I don't know if any of you guys have gone by it. If you're maybe like driving to Target from downtown, you actually pass by it. It's on L Street and like between maybe 3rd and 1st Street. Off on your right-hand side. Yeah, and then individual services are then provided electricity by distributing from the substation through your distribution lines. Those are the wooden poles, and then through either pole transformers. Those are the sort of silver or green cylinders that you see, or by transformers that are on the ground. So that would be these big green boxes. Yeah, and so again, I think most of you guys are familiar with seeing this sort of infrastructure around. So the basic components of the distribution system. So in Davis, this is a view of our distribution grid. As I was mentioning, sort of on L Street, this is the Davis substation. From the substation, you have these lines going out. You can see a bunch of different colors here. Each of the colors represents what's called a distribution feeder or circuit. And those are essentially not independent systems, but localized circuits that the substation is essentially balancing. And so you've got, maybe a dozen or so circuits in Davis. And this is PG&E territory. One of the things you'll notice is that there is a distinct lack of circuits on the UC Davis campus, and that's because UC Davis doesn't actually operate with PG&E. They operate with a different utility called WAPA, and so you don't actually see the substation or the distribution infrastructure for UC Davis. And just to give you guys a sense of what you pay for in terms of your electricity, of those three sort of main components, I mean, obviously there are other things that you're paying for in terms of service, like with utilities and certain other services that are being provided, but the majority of your electricity bill can be sort of broken down like this. On average in the US, it might be a little bit different in California, but I wasn't able to dig up any numbers about what the breakdown is in California. But you've got generation at about 2/3, and then distribution and transmission slightly smaller, with distribution being maybe twice as big as transmission. And so that's more of the sort of traditional grid. I think there's a big movement towards distributed power and sort of disconnecting from the traditional grid. So thinking about things like microgrids or smart grids you may have heard of. We're not going to talk too much about this, but the concept is that if you are traditionally sort of connected with big power plants that transmit power over long distances, the more sort of new way of thinking of more localized power is having things like local battery storage, having lots of solar, and being able to sort of distance yourself from relying on the larger electricity system as a whole. So I think it's a pretty well studied topic. There's a lot of work going into it, and I think definitely there's a movement towards this sort of system in the future. But I also think we're probably a little whiles off from a total disconnect from the sort of traditional grid as we think of today, and more likely it'll be some kind of integration between the two. Okay, I wanted to talk following this primer on our electricity grid about kind of the fascinating world of electricity regulation. And so, we are starting to wrap up our discussion about basics of energy technology, demand and supply, and thinking about how it gets produced, how it gets used, and starting to tie it a little bit more in with policy and regulation. That is kind of the aim of this course. And so as we've set some of these foundations, I think we're going to start to dive more and more into regulatory issues and policy issues. So I think this is kind of a good place to start off. It's an area that's really rich in issues and regulation. And you do kind of have to know some of the basics of how it works and issues in order to have a meaningful conversation about a lot of the policy aspects. And so hopefully we've built that up by now. So when it comes to electricity regulation, it's a pretty rich area of discussion, and there are a lot of stakeholders involved. So everyone everywhere from government, so that's legislature, regulators, and then on the more local level, municipalities, but we can even go down to county or city level government as well are involved. Obviously utilities, so we'll talk a little bit about what it means to be vertically integrated versus competitive. The folks who own generator assets, right? And so that's not the utilities who are often forced to divest from generators. You've got vendors, customer groups, and NGOs. All of these are important stakeholders in understanding sort of electricity policy. So why do we even care? Like, why does it matter that we want to regulate this industry? So one, cost recovery. So this is one of the ways that we can make sure that utilities are actually able to recover their costs, right? So if you studied economics at all, one of the big things to keep in mind with imperfections in the market is the barrier to entry, right? And so if you think about power production, the barrier to entry is really quite large in that it costs a lot to build the infrastructure, it costs a lot to build the generators. And so even though, I think these days, even though you may feel a lot of hatred towards maybe PG&E for like poor business practices, on the other hand, you do have to recognize that, like, if we didn't have PG&E, that would also be a pretty big problem, right? And so you do want to be able to walk this fine line of making sure the utilities are doing what they want, or not doing what you want, not what they want, but also making sure that they kind of stay in business. And so that relates to the cost recovery portion. Rate design. So how much are you paying for electricity? Have you ever felt it's unfair, electricity is too expensive, or that California electricity is much more expensive than most places in the country? And so how are the rates set? So that's actually through the Public Utilities Commission, and they try and do a really diligent job of making sure that the rates are as cheap as possible, especially given that you may have some sort of monopoly type issues, right? Because the barrier to entry is so high. Um, at the same time, they want to make sure that cost recovery is able to happen. And so anytime a rate increase happens, like PG&E wants to charge a little bit more money, they have to go to the Public Utilities Commission and justify why they're allowed to increase the rates. And that often turns out to be a pretty big fight, or can be a pretty big fight. One of the things that, at least in the US and in California, is this idea of obligation to serve, where we think of electricity as kind of a public good. And so we want all customers to have reliable access to electricity, which not only means that it should be cheap and accessible, but also, like, I can't be paying for a service that is like blacking out all the time, right? Because I could be paying the correct rates. I could be paying my 17 cents or 21 cents a kilowatt hour, but then I could be having like blackouts every other day. And so there are obligations that are independent or somewhat independent of the economic aspects. And then on the supply side, you want all generators to have competitive access to electricity markets. So this speaks to that like monopoly issue, is you definitely don't want like one company sort of just crowding out all the others and then being able to set whatever prices that they want, right? So that supply curve that I was showing earlier with the dispatch curve, that only works in a competitive market, right? And if it's not competitive, then you could have a bunch of generators get together and collude what prices that they want to set. So you definitely need open access. This has been a really hot topic for the last sort of 20 years. So electricity market restructuring. So before restructuring, or we also known as market deregulation, you would have a single utility be able to own all three major aspects of the market. So generation, transmission, and distribution. So PG&E used to own the power plants as well as the transmission as well as the distribution. And you can probably see potential monopoly issues with this, right? Because if you own all of the infrastructure, then you can sort of dictate the terms of how much things cost to provide through the system. And so when PG&E was able to own all of this, we had what was known as a regulated market. So because they owned all of these and we didn't want them to be just a monopoly, we set really strict rules about, you know, what the rate structure was, and then some sort of operational constraints on the different aspects of the electricity grid. Since then, a bunch of states have deregulated, and in doing so, you now worry again about market power issues. And so what they did was that they no longer allow this vertical integration or ownership across all the structure, all portions of the system. And so PG&E was forced to divest from a lot of their generation assets. So almost all of it was sold off. And then they had to allow non-PG&E generators to have access to the transmission and distribution systems. And they get paid still from other generators using their systems through the from rate recovery, essentially. So just to give a sense of kind of what that looks like in the United States, for regulated markets versus deregulated, So the dark blue, I think, are the ones that we really care about for deregulated, and the striped ones for deregulated markets. And so there's been a very sort of lengthy conversation in the electricity industry and in academia about whether or not deregulation is good or bad for utilities, for customers, and I think that uh, there isn't necessarily a clear answer. I think a lot of studies have pointed to um, regulated markets being better for a small period of time, and then a whole bunch of studies came out that said deregulated markets were better. So I'm not necessarily clear on the answer, but it's definitely led to a lot of interesting discussion about what the right way to do it is. Okay, so kind of backing out again up to a high level in terms of policies. When we think about the types of environmental policies that we care about, so promoting renewables, decreasing emissions, demand side management, and so this is demand side management really on the side of consumers. Um, uh, this is essentially reducing energy use. And then the last one for electrifying transportation. There's a whole slew of policies down here that you can see: renewable portfolio standards, solar initiative, for renewables, for emissions, things like cap and trade. And so some of you guys, I think, are going to help be able to enlighten us with some of these policies, which are being covered as topics for the group project. But we'll actually dive into a lot of these as we transition into thinking about specific policies in lectures. And so those were just the environmental ones, and then you've got a whole slew of economic policies. So this is, I think, a little bit more specific for the electricity grid, as opposed to other parts of the energy system like transportation. But retail competition. So I know one of the groups is going to be doing community choice aggregation. So we'll learn about that. But there's a whole slew of economic policies to think about in the world of regulation for electricity policy. So who are the players? So the utilities, as I've discussed, so PG&E in most of Northern California. You've got Southern California Edison, which does most of LA, and then San Diego Gas and Electric, SDG&E, for San Diego. These are essentially fully regulated monopolies because they own all of the transmission and distribution, but they're not fully vertical because they've been decoupled from the generation, and so the electric service is separated. And then you've got regulators. So I've talked about some of these throughout the course of today and in other lectures of this class. So the Public Utilities Commission, so that's known as the CPUC. So they regulate the economic and operational aspects of the utilities. California Independent System Operator, CAISO, they regulate the wholesale generation and transmission markets. So all the power plants and all the big transmission system is operated by CAISO. These are the guys who take in the bids from the generators and decide who gets to turn on. The California Air Resources Board, or CARB, they regulate emissions and air quality from all of the point sources. So if you are operating a fossil plant in California, you are responsible for reporting emissions to CARB and following any rules that they might have. pertaining to stationary stationary emission sources. And then lastly, California Energy Commission. So they regulate power plant siting and energy efficiency standards. So in terms of who does what, CPUC, CAISO, CARB, and the California Energy Commission. So this is the different portions of our electricity system. You've got your generators, transmission, distribution, and then end users. So the CPUC kind of has their hand across the full spectrum of the electricity grid. So generation planning and contract approval, transmission planning, distribution planning, and then rate design for customers, as well as like customer programs. So a lot of like efficiency programs that might happen, that could be something that comes out of the CPUC. So to give a more concrete example of that, so that I don't think this is actually CPUC. I think it's more federal, but the Energy Star Savings Program, that might be something that you would see supported by the PUC or maybe by the California Energy Commission. But those are the types of customer programs that we're talking about. So some examples of this: general rate case, planning and procurement. So when we think about how much capacity is needed to meet demand in the future, they can do some projections of this and help develop the plan and procedures for utilities to build new power plants. And this is getting more and more complicated due to the integration of renewables with more distributed rooftop and getting that to align with the needs once you account for rooftop solar with the utilities. Net metering 2.0. So this has to do with developing a program for getting net metering to work, which is the concept we talked about earlier this lecture. And that decides on how much money people are allowed to make, and essentially all the related regulatory aspects of net metering. They're responsible for distribution safety. And so a lot of that infrastructure is kind of just in the public areas. And so CPUC is one of the entities that's responsible for ensuring safety standards and protocols are met with regards to the use of distribution infrastructure. For CAISO, as I was mentioning, they're mainly on the wholesale side. So this is speaking with regards to the power plants and the transmission system. So transmission planning process, ensuring that we have competitive markets, and they also are responsible for the import and export of electricity in and out of California. So they manage the jurisdiction between states of electricity transfers. California Air Resources Board, they're mainly on the upstream for environmental planning and emissions markets. You might consider them on the end users as well, although that would definitely be a little bit more hazy, I would say. Cap and trade is a topic that we're going to talk about, and actually it's one of the group projects as well. It's one of the big carbon emissions policy tools in California. I won't go into this too much more because we'll talk about it later. They're responsible for a scoping plan for climate change, and so a lot of the state goals that are trying to meet climate change goals, that's being done by CARB. They're the ones who've put together the program for electric vehicle incentives, so that's why I was saying certain parts of it are kind of on the end user. And lastly, the California Energy Commission, they do a lot of the planning and siting as well. They do a lot of demand forecasting for customer programs, and they provide subsidies for a lot of the customer demand side management programs, such as energy efficiency. Yeah, so generation siting and permitting, energy efficiency standards, independent energy policy report. So this is, yeah, exploring how the demand and resources can align in the future. Yeah, so I feel like I've kind of breezed through a bunch of these regulatory agencies, and this is to give a high-level picture of sort of the necessary, regulatory process. It's very, there's a lot happening. There are a lot of stakeholders, even within one category, right? We were just looking at the regulatory agencies that are involved. And I think that speaks to both the complexity and necessity of having good policy in place to make sure that the system is operating in a good way. And but I do want to emphasize that it does lead to a lot of complexity. I'll give kind of an example of the number of stakeholders that can get involved in a particular policy. So this is a law called SB 350, which commits California utilities to achieve 50% renewable generation on average in 2030. So in 10 years, half of all of our electricity is going to be coming from renewables. And you've got, like I was saying, a lot of different players here. So you've got legislators, you've got folks in the utility, you've got a bunch of, or a couple environmental groups that are involved. Yeah, so lots of different players that get involved in this thing, and I think that's a really good thing. When you put together a law, you want feedback from lots of different stakeholders to make sure that you're getting right, and you definitely don't want it just to be getting influence from one direction. You want direction from as many groups sort of as possible. Yeah, bill signings don't always look like this, obviously, but this one was particularly important. And because California and former Governor Jerry Brown puts a lot of emphasis on clean energy and climate, they had this pretty interesting signing process for this bill. Yeah, so I guess we'll leave it at that for today. We'll end on this, just wanting to show as we transition into talking more about policy for energy that it's pretty complex, lots of players, and I think it's going to lead to some pretty interesting future lectures about how we put all this together. Okay, I see a question. Will other states also have a similar system like California? Yeah, so okay, so this is kind of like a question about California versus everyone else. Definitely other states do other things, and we are not only going to focus on California. We'll talk about things that other states are doing, things that happen at the federal level, and even things that happen in other countries. I will say that I think California is a particularly progressive place as it comes to, with regards to energy and climate. And there are countless examples that we're going to point to where other states and even the US or even other countries have followed in the footsteps of California. And so even though we think of California as, I mean, it's not that small of a state, but compared to countries and at the country level, we are kind of small. but California really is one of the big leaders in this space, in the sense that what we do, oftentimes other people will follow. Yeah. So okay, there's another question on the homework. So I'll answer that. So question 5 on homework 2, converting to primary energy use. Yes. So essentially, you just want to change everything into the same units and then convert it from the end point, the final energy, into the primary energy, which you just do by multiplying by, yeah, the 40% or 90%, depending on what the source is. So you need to do the right corresponding conversion so that you get the efficiency right. And yeah, so that'll let you both compare them, but it'll also let you add everything up sort of on the same level. So you can do, I don't remember the question exactly off the top of my head, but probably the things that would make the most sense to show would be that the total energy in terms of primary energy, and then you could also have like a table that lets you compare across them. Okie dokie. Well, thank you, everyone. And if there's no more questions, I will see all of you on Monday. Okay, wait. I do see one more question. Can we say no no gasoline or natural gas because no one's driving around anymore? Yeah, that's totally fine. And I kind of expect that actually there's going to be very little gasoline consumption these days.